Let's go ahead and get started. My name is Praveen Rokhaya. I'm the science coordinator of the Global Water Futures Core Modeling and Forecasting team. Today, it is my pleasure to welcome Dr. Mary Amélie Boucher, who is going to present a webinar on making the most out of models and observations for a better portrait of snow in Quebec and Canada. Dr. Busek is an associate professor at the Department of Civil and Building Engineering of the University of Sherbrooke in Canada. She was previously an assistant professor at the University of Quebec at Chicoutimi from 2011 to 2017. Dr. Busek is also serving as one of the co-chairs of the Hydrological Ensemble Prediction Experiment, also known as HEPEX, since 2019. Our research mainly focuses on hydrological ensemble forecasting and more precisely on data assimilation, pre and post-processing, innovative use of machine learning techniques in hydrological modeling, forecasting, forecast communication, and the value of hydrological forecast. I believe she will be highlighting some of these works today. All right, without taking much time, I want to kick off this webinar by thanking Dr. Busek for accepting our invitation to present in this webinar series. The webinar today would be about 45 minutes of presentation, followed by 15 minutes of question and answer session. Dr. Busek, the floor is yours.
Okay, thank you very much. Thank you everyone for attending this webinar. So this will be a presentation about data assimilation for snow. And maybe the particularity of what I'm presenting is that we want to assimilate snow and to model snow on a very large territory. So mostly, almost the entire province of Quebec. And our goal eventually is to do the entire country, so the whole Canada. Oh, I cannot change slides. Okay, all right. So there are many problems with snow, but snow is also super important for flood forecasting in spring here in Canada and also in many other parts of the world. So basically, some of the problems with snow is that we don't have enough information, not enough observations in space and time. So here in Canada, we have a very large country to cover, so we cannot monitor snow on the ground obviously at every point in space. There are alternatives for that, of course, so we have satellite data that maybe can help us. But there remains a problem that we don't have enough observations in space and time, and snow is a variable that has a lot of variability in space and time also. So this series of projects initially started by a request from the provincial government, because they are the ones responsible for flood forecasting here in Quebec. And they were not happy with the way their model was representing snow, not completely happy. And they were also not happy with the way they were using the available observations. So for instance, one of the issues for them is that they were only using the observations from manual snow surveys. So people who go out there in snowshoes and collect snow samples to measure snow water equivalent and snow depth and so on. So in Quebec and in many other places, there also exist other instruments which are installed at ground stations, so ground meteorological stations. So an example of that is sonic sensors. So this allows to have automatic measurements of snow depth continuously. But since those instruments measure snow depth and not snow water equivalent, before starting this whole series of projects, they were not used by the government, and they were not happy with that. So they wanted to use more of the data that was available and find ways to kind of all put that together, the model and the different sources of data. So I already mentioned that. So those two pictures, they show at the left a sonic sensor. This is the part that is circled on the figure. And on the right, you can see an example of people taking manual snow surveys. So what we wanted to do to kind of combine everything together, we wanted to use a particle filter. So instead of explaining the particle filter with all the mathematical details, I will just explain it more conceptually using this figure here that you see. So what we do when we want to implement a particle filter is that we have to first generate particles. So particles, what they are just basically scenarios. So on the figure, they are represented by the colored dots at time t. So you see a vertical line with all those colored dots. So those are the particles or the scenarios. And to obtain those scenarios, there are different things that you can do, but basically you pretty much always have to add perturbations to different elements of your model or your data. So you can, for instance, add perturbations to your meteorological inputs, the precipitation and temperature, and maybe some other inputs. And you can also add perturbations to the product, the end product of the model. So for instance, snow water equivalent, that would be the output of the snow model here. So you obtain those particles, and those particles, they can move through time. So they can evolve through time using the model, the snow model here. So, and maybe at time t+1, so later on, you will have some observations that are available and that you can compare with your particles. So at time t+1 on the figure, you see that we have two different observations that became available. So we have the observation from the manual survey, the snow survey, and this observation is also uncertain. So that's why it's not represented as a line, but rather as a probability distribution function in gray. This is to represent the uncertainty. And you might also have another observation from another instrument, for example, the SR50, which is a type of sonic sensor. And this is also associated with an uncertainty. So again, it's a probability density function. So what you want to do is to weight your particles or your different scenarios. You want to weight them differently according to how close or far they are to your observations. So for instance, if you look at the particle that is represented in green, it's pretty much at the center of the observation from the snow survey. So this one will be given a large credibility or a large weight. And the red particle, which is at the bottom, it's very far from both observations. So this one might either be discarded or given a lower weight. And then you can resample. So for example, if you look at the third vertical line, you see that some particles are kind of now overlapped. So we have a resampling according to the weight. So for instance, I mentioned earlier that the green particle was given a large weight. So to kind of represent that, we could resample around that particle. There are many, many ways to do this resampling. There are many varieties. And then we will just continue. So we will run the model again. So this will all continue to evolve in time. And yeah, this will continue like that. So there are not many issues about applying this for a single point. But things can be more complicated when you want to apply this idea, this particle filter, to a very large territory where maybe you have only certain observations available at certain points in space and also in time. So this is our specific framework for what I call step one. So in step one, we started just by assimilating data from the manual snow surveys only. So no SR50s in this one. It's only one type of observations. And we were using a component of the hydrological model that is used operationally at the province of Quebec for operational flood forecasting. So the model, the hydrological model, is called Hydrotel, but we were not using the entire hydrological model, just the snow routine. So I will provide a little bit more detail about that later. And on the figure, you can see the data that was available. So this is the, those are the observations. So the manual snow surveys from various organizations that kind of pool their data together. And you can see the data that was used for calibration and validation. And in fact, in this particular study, we did two types of validation. So one was a leave one out validation, cross-validation, and one was really a validation where you have a separate calibration portion of the data and a validation set, which you can see on the figure. So about Hydrotel's snow routine, it's a very simple model. It's a degree-date model with 6 parameters. Those parameters were calibrated globally. So this means that the calibration was designed to perform well overall on the entire province. So it's not like point by point or basin by basin. It's on average for the whole province. It has 5 state variables, including snow water equivalent, and it requires some input data, which are precipitation and temperature, and those data are provided on a grid. So it's a 10 kilometer by 10 kilometer grid, which is obtained by cridging all the ground stations on a regular grid. And we did use that in this framework. So we wanted in the study to account for the spatio-temporal variation and the spatio-temporal coherency of all the perturbations that we were to apply on our particle filter in order for us to be able to interpolate the particle weights. Because what we're going to do is that we're going to apply the particle filter at specific points in space, which are the points where we have observations available. But then we want everything to be applied in a coherent manner in space and time so that we can then interpolate those weights on the same grid that is used for precipitation and temperature to obtain a grid for sweep, snow water equivalent. And this would then allow us to have a portrait of snow or to estimate snow at some points where we don't actually have any observation. And well, of course, you might say that 10 kilometer by 10 kilometer is a very coarse grid. It is, but at least it's coherent with all the rest of what people do at the provincial government. So yeah, and it's kind of how it's based there for hydrological forecasting. So everything is on the same grid. Okay, so this is a bit of the mathematical part. Like I said, I'm not going to provide all the equations for the basic particle filter, but maybe just some equations that represent some of the specificity of our particle filter. So we have a measurement noise that we need to account for. So the snow surveys and the SR50s, in this case, it's only the snow survey for this one, they necessarily have an uncertainty. And this uncertainty has kind of 2 parts. So there is the on-site measurement uncertainty, so really the one that is associated to the instrument, and it's probably very small. So on site, the measurements are probably quite good. But then, since our grid is very coarse, we have a very important spatial representativeness uncertainty also, because we are considering that a single point is somewhat representative of a larger portion of territory. So you see the equation defining how we define the measurement noise. And here in this equation, y is an observation, and x is the state vector of the model, not the hydrological model, but the snow model at time t, and according to a specific particle. So it's basically drawn from a normal distribution, this measurement noise. And so you can see the definition of the mean and standard deviation. So the sigma here, you see that there is a 0.2 in there. So this value was just obtained by calibration for this. Then we have to have some process noise. So the process noise represents the model uncertainty and also the uncertainty that comes from the meteorological observations. So this is our grids, the grids for observed precipitation and temperature. So for SWE, which is the output of the snow model, we just use the multiplicative uniform perturbation. And for the precipitation and temperature, because we wanted to keep this spatial temporal coherency, we decided to use an additive noise that follows a Gaussian distribution, and the variance of this Gaussian distribution would be the Kriging variance. So this one is not calibrated, so it's more objective. It's not to say that this is the true uncertainty on precipitation and temperature, but at least it's not calibrated, and it's coherent again with the precipitation and temperature that is used in the model. Then specifically for the spatial-temporal coherency in the process noise, we added two components. So one is a temporal correlation. We took that from Evanson 1994, and you can see the equation here. And we also included a spatial correlation after Uboldi et al. 2008, sorry. So this ensures that the perturbations that we add on the meteorological inputs and also on SWE are correlated, have some sort of relation with themselves in time, and also that the different cells of the grid have a correlation with them. So the perturbations that we apply on one grid cell is related to the perturbation that will be applied on the neighboring cells. And again, some parameters in that, for example, the 20 days for the temporal correlations and the 300 kilometers for the spatial correlation, this was again optimized. Not really optimized in a mathematical sense, it was mostly trial and error, but we found, for instance, that above above 300 kilometers, it did not make any difference, and that this value was probably the good one to use. Okay, so this is for the more theoretical part or the explanation part, and now I want to show some results for this portion. So the figure that you see here is a portion of the validation. So I mentioned earlier that for this study we had two types of validation. This is mainly because of one of the reviewers of the paper who wanted completely different validation and a completely independent data set. And at the moment of submitting the first version of the manuscript, we did not have such an independent data set because we had already used all the data at some point. So this is the first validation. So this is a leave one out cross validation. And what we can see here is the distribution of different metrics for all the grid cells over all the province. So for instance, this is the cumulative probability distribution for the Nash-Sutcliffe efficiency criteria. And we would like all those lines or those curves to be towards the one. Okay, so the yellow line, the yellow curves, represents the particle filter that is applied at the same location. So it's not really specialized, this one. And it's used more as a reference, but it's not really what we want to do here, because we want to specialize everything and be able to assess the snow water equivalent, to estimate snow water equivalent at unobserved location. So the yellow line is really here only for comparison. So it's a particle filter, but applied at the same location, where always at the same location. And the blue line is the open loop. simulation. So that's where we start from. This is without any data simulation. So what we are mostly interested in here are the red-orange curve and also the green one, which is the proposed spatial particle filter. So the orange one, the orange curve, is the previous method that was used at the government of Quebec, which is basically direct insertion. So when they would have snow surveys that become available, they would just insert the value and then continue running the model. So this direct insertion plus optimal interpolation, it's good. Okay, it's a valid method, but what they didn't like with this method is that they did not see how it would allow them to kind of merge different types of observations together, and also to they found that it required a lot of interventions from the human forecasters also. So they were not happy with this method, but it did provide good results. So that's what we see here. And we see that the green curve is very close to this one, to the orange curve. So we do at least as well as the direct insertion method, but maybe even a little better. But then we have the other validation, and this is a validation on a completely different validation data set that we managed to obtain after the first version of the manuscript was submitted. So actually, when we received that comment from the reviewer, we were very happy to have obtained those new data, because then we could apply the suggestion. And we were honestly a little bit lucky, I think, with those data, because if I go back a little at the beginning, and you can see the map, those red points, they represent the location of those new points, those new data that we obtained in the meantime. And as you can see, they do not have really the same spatial distribution as the blue crosses that we had initially. And I think that, yeah, it's not completely unbiased, the sampling here. But for us, it was a little bit advantageous, because as you can see here, if you look, for instance, at the Nash-Sutcliffe efficiency for this particular independent data set, our specialized particle filter actually outperforms the direct insertion, and it's more visible than in the first validation, which was a leave one out cross validation. Okay. So we were very happy with that. We also verified that we could indeed preserve some form of spatial structure. So this is just an example for a portion of the territory. So for 2 different dates. February 8, February 9 here. So we have the open loop simulation, what it looks like in that portion of space. This is for sweep. And then you have what you obtain with the direct insertion and with the spatial particle filter. So there are some differences, of course, in the spatial pattern, but the main message here is that we do preserve a sort of spatial pattern in our particle filter, even though we apply it at some points in space, and then we interpolate the weights elsewhere. Okay, so this is the publication that we have about that. And then we wanted to move towards assimilating also the SR50 data. But we thought that it would be a good idea to first convert snow depth to sweep, because SR50 or sonic sensors, they measure snow depth and not SWE directly, so that's a bit of a problem, and we did not really want to assimilate 2 different variables from 2 different instruments at the same time. We preferred rather to bring everything into snow water equivalent before. So to do this, we first did a small exploratory study about using multi-layer perceptrons. It's a form of neural networks to convert snow depth to sweep. So here you have an illustration of a neural network, a multi-layer perceptron, which in fact here has only one hidden layer, which you can see here. So for those of you who are not maybe familiar with neural networks, how it works is that you have your inputs here. So for instance, for us, the relevant inputs could be meteorological data. Of course, snow depth would definitely be one of the input. It's kind of the main one, but you could also have solar radiation if it's available. Basically any input variable that you think could be relevant for your model. And then you would have some parameters. They are called weights and biases, but they are not weights and biases in a real statistical sense. That's just their name, okay? So weights and biases are the parameters of your neural network models, and they have to be calibrated or trained in the vocabulary of machine learning. And in the hidden layer, you have to have what they call an activation function. It can be many different types of function. So here you can see the different features of how our first experiment on this. So for us, the activation function was the hyperbolic tangent. So you have one such function in each neuron of the hidden layer. And then again, some weights and biases, and then the output, which would be snow water equivalent here. So there is an uncertainty in that type of model also, because the parameters, the weights and biases, they are normally initialized randomly and then they are calibrated. So there is an uncertainty related to that. And to represent that, what we did is that we had an ensemble of 20 artificial neural network with a random initialization of parameters, and then they were trained, but they were not trained until they were like identical. So we stopped a little bit before. So oh yeah, in this case, I said the output variable was snow water equivalent. It's not true for this one. So it was density, so rho here, and we could obtain snow water equivalent by, of course, multiplying the density with snow depth. So this is for this first design. And we wanted to compare that with some alternative models. So the Sturm equation and the Jonas equation, which are two simple regression that are popular in the literature to convert snow depth into sweep. And we did many tests. So for instance, we wanted to test if having just a single artificial neural network for the whole province would work well, or if we could instead train regional neural networks. So you see the map here with the different hydro regions in the province. And then you have also the input variables that we tested. And for each trial, we computed the RMSE on sweep. And then overall, we decided that the input variable snow aging, so this was basically an amount of days since the last snow, it was not really useful according to the RMSE, so we decided to remove it. Those equations here that you see, the 6 and 7, they are just the regression models that I was mentioning before. So the Sturm equation and the Jonas equation. Those are our benchmark, if you will. So some graphs of the result. So first you have the estimated density as a function of the measured density, and you can see that it's really more like a cloud. It doesn't really match completely with the line. So density is a very difficult variable to model here. But then when you convert that into sweep, because of the strong correlation with snow depth, it's better. And again, if you see at the numbers for the RMSE on sweep, and you compare the Jonas and Sturm models with our proposed neural network model, you see an improvement on the RMSE. So we have a smaller error than those two regression models. And there was also another model, very, very simple model that we decided to use. It was to consider two densities that would be constant. So one density for the accumulation phase and one density for the ablation phase. And this one, without any surprise, it was the worst performing one. So some more details on that. So in those graphs, we see the same type of plots. So density against density, the estimation and the measurements, and the same for sweep. And on the left side, you have the results for our multi-layer perceptrons. And on the right, you have an example for a Sturm model. So even if our method still has this cloud of points for estimated density versus measured density, it's still a little bit better than what we obtained with Sturm, because as you can see, you have more points kind of away from the line using the Sturm model. So this explains the improvement that we get using our method. This is some more comparison. Something interesting here is that when you plot the measured sweep against the measured depth, you see some variability, and maybe more variability that we have when we use either our method, the MLP method, or the Sturm method. So for the same measured depth, because the density does not depend only on depth, and it depends on a multitude of factors. For the same depth, you can have many different values of SWE, and that's what it is difficult to capture with the model. But this was very encouraging, and we published a first paper about this first kind of proof of concept that that using neural networks to convert snow depth to SWE was maybe a good idea. But we decided to continue further with that. And so we did a more exhaustive study, but on the same topic. So, and also we extended the spatial coverage of the experiment. So this time we wanted to cover the whole country. So this was for the entire Canada, and you see the blue points here that represent all the data that was available, so that we could use for the study. And you also see the different type of snow regions that we used. So in the first study, we used a separation according to hydro regions. But this one is different. It's according to the type of snow. So it's a classification, again, by Sturm, I think. I did not put the reference here. I'm sorry for that. And as I said, we wanted to test many more options, if you want. So options in terms of input variables, in terms of activation function, in terms of target variable, because the student that worked on this study was really disagreed with the idea of having density as the target variable, because he said, why not have SWE directly? So he tried that. And basically this table shows you everything that was tested. So he worked a lot on the optimization algorithm, and that's one thing that really, I think, made a lot of difference, because in hydrology, oftentimes when we use machine learning, we use the Levenberg-Marquardt training algorithm. So this is the algorithm, the optimization algorithm that is used to adjust the parameters of the neural network. So the weights and biases I was mentioning earlier. So this is really a very, very popular optimization algorithm for that purpose in hydrology. But Constantin, the student working on the follow-up on this, to apply that over Canada, he found out that actually Levenberg-Marquardt is not a super good algorithm. It has lots of problems with local minimas and lots of other weak points also. So he decided to try other algorithms. And yeah, you have the list of things that were tried. He also decided to test a different way of organizing data during the training. So he would use those mini batches during the training. So he would separate the available data in very small groups and use only one or a few of those groups for an iteration of the training, and then switch to another group of data for the next iteration, and so on. So we really went into the details of the architecture and all that could be improved in our neural networks. So we also tested, okay, so this is a sort of monitoring of what happens with the number of epochs. And on one side, so in column A, it's for when you use, if I'm correct, snow water equivalent as a target variable. And on the B column is when you use snow density as the target variable. So this is a monitoring of the evolution of the ensemble of neural networks with the epochs. So epochs is just a neural network vocabulary way of mentioning iterations. So yeah, so actually I think I said the reverse. So A, the column A is with snow density as the output variable, and B is with SWE as the output variable. So we also tested different number of input variables. We had a list of potential candidates as input variables. And so we monitored the error in terms of SWE, the CRPS, also the logarithmic score or ignorance score as a function of those variables, input variables. All of this to kind of fine tune our architecture and setup. So there are a few tables that present the final setup. This is actually the number of records that were available for each type of snow, the number of epochs that were used for the training, and the number of hidden neurons in the hidden layer. So that's different from for each category of snow in our case. And this is also the final setup for two proposed frameworks. So SMLP is a single multi-layer perceptron, so just one architecture for the whole country. And MMLP is a multiple multi-layer perceptron, so it means that we have one for each snow class. And then you have the target variable, whether or not we included some input uncertainty on the snow depth, the activation function, the optimization algorithm that was selected in the end, parameter initialization, and so on. The batch size, number of members, etc. And there is a comparison with what we had in the first paper with Audrey et al. So this has evolved quite a lot. And with all those improvements, we were able to obtain also some improvements on the results. So you see, for instance, the simulated SWE compared to the observed SWE, and you have the results for both the single MLP and the multiple MLP at the bottom, and you see that it's a lot better than when using the Jonas and Sturm model, or again the simple benchmark. So this is also published. This is not in discussion anymore. This was published a little bit earlier this year, or I think maybe at the end of 2020. And now that we have a method to convert snow depth to SWE, we wanted to include that in our particle filter. And this is something that is not yet published, but it's pretty much ready. We're just waiting for linguistic revision. So you see here the data in red for the snow survey, for assimilation and for validation, and also in green the data from SR50s. So obviously the advantage of using of adding data from SR50 is that it allows for a better coverage. I think I'm running short on time, so I will try to go a little bit faster. or maybe skip some details. So when we started assimilating SR50s, we quickly noticed that there would be one problem. So when we only had manual snow survey data, we would have observation data available once every 2 weeks, which is not very often. And we would resample, we would do the particle filtering at that moment. Now with the SR50 data, we have data that is available continuously. So we could assimilate with a very, very high temporal frequency. And this has some consequences, which are, and one main consequence, which is illustrated here. So the different scenarios, the blue, red, and green grids that you see at the top, they represent different particles. So particles are scenarios. So for instance, the blue grid is one particle, and the red grid is another particle. But when you perform the particle filter, you have to weight your particles and you have to do a resampling, because when a particle is attributed a high weight, you want to resample around that particle to represent the fact that it looks good, this particle. And you do that not for the whole grid, you do that point by point where observations are available, because otherwise, I mean, on a grid cell where you don't have any observation, there is no way that you can judge about the quality of a particle. And also, since it's a very large territory, the province of Quebec, there is no way that one particle could be the best one at every point in space. So we could not, for instance, say that the blue grid is the best overall for all points where we have measurements. So we resample locally at each place where we have an observation. So the result of that is a loss of spatial coherency. So we lose the coherence in the spatial structure because we resample locally. So that's what is illustrated in the other figure. So you have a mix of green, blue, and red. And really this doesn't work well. We want to end up with a map of snow water equivalent that remains coherent in space, even if the tiles are very large. So of course there is an uncertainty for that, but at least it looks coherent in space. So we had to work on maintaining that. So what we did is that we implemented and we compared two different types of reordering of the particles. So what we decided first to do, it was to say, okay, on a given grid cell, we will just reorder the particles in ascending order. So we will just kind of sort the particles so that the smallest one is also accompanied by the smallest ones for the neighbors, the neighbor cells, so that it would remain coherent. So it's just really a sorting of the particle for each grid cell. So it's a very, very simple solution. And the outcome of that, I just want to say the right thing, so I have to check. Okay, so the figure A is the open loop. Okay, so there is no particle filter here. It's just the open loop simulation using the snow model. In B, there is no reordering. So in B, this is what happens when you perform the assimilation using the SR50 data, but you don't really preoccupy with the spatial coherency, and you don't do anything special about it. So what you can see is that on the edges of the contours, they're a little bit fuzzy, if you want. So we see that maybe there is something going on. So on the C panel at the bottom left, this is our simple sorting of the particles. And of course, the specific patterns are a bit different from the open loop, but that's expected because we are assimilating data into the model. So of course, it cannot remain the same. But what we're looking at is that the edges of the contour, they are better defined, if you want. So it looks more continuous in space. So we are inclined to think that this is probably more realistic as a representation of snow water equivalent. And the D panel is a little bit more sophisticated way of doing the reordering. So it's an adaptation of the Shaky Shuffle. So the Shaky Shuffle was proposed to regain the spatial coherency of a map of precipitation after downscaling. So to perform this method, it's also a reordering, but it's a reordering according to historical data. So the problem here for us is that, contrarily to what would happen with precipitation, we did not have historical grids of snow water equivalent. So we basically had to build ones, but we said, okay, we could use the open loop simulation, because even though we know that it can be improved and that the model is not the reality directly, maybe the model is at least able to preserve this spatial coherency. So it's a modification of the Shaky Shuffle because we build our historic ourselves, and then we use that to reorder the particles. So after that, we also verified how frequently we could assimilate and perform the sampling and the reordering. And generally, what works best is to do everything at the same frequency. So, for instance, you see the open loop, and you see you see the RMSE. So we want to have the lowest possible RMSE, of course. So the green curve represents an assimilation frequency of 1 day, which is coherent with the sampling frequency and the reordering frequency. So that's what provides the best results. And similarly, if we are to assimilate every 7 days, so approximately every week, we would have to do the sampling and reordering at the same frequency. So I think I will have to go very quick on that, but basically this is a comparison of what happens when you assimilate the SR50 or the manual snow surveys. And I have also another figure, maybe this one is better, another figure related to that. So open loop, snow surveys only in orange, SR50 only in yellow, and both type of measurements that are assimilated in the snow model at the same time in purple. As you can see, everything is very, very close for most of the performance metric. And what works best overall, but only by a slight difference, it would be to assimilate only snow surveys. This is because snow survey, they don't have this uncertainty related to converting snow depth into SWE. We kind of trust those measurements more. But you can also see that the yellow line, for instance, if you look at RMSE, the yellow line, which represents assimilating only SR50s, is still closer to 0 for the RMSE than the open loop. So the message from that is that if you have manual snow survey, it's the best thing that you can assimilate, at least compared to SR50s. But if you only have data from SR50s, it's still worth it to assimilate them in your model. So you can still have some gains from that. So now where we are at this point is that we want to assimilate the SWE, the grids for SWE that we have into the rest of the hydrological model, if you want, and see if this will improve the simulations, but also the forecast. So we're looking more at long-term hydrological forecast here with two types of models, so Hydrotel and HBV that is implemented in Raven. So we have a project about that on that topic with both the provincial and the federal government. And another thing that I would really like to do in the future, two things, would be to add snow data from citizen scientists, and also to compare our SWE maps with the data from SNODAS, which is used a lot in practice. So I hope I did not Yeah, I exceeded the time a little bit. Sorry about that. I would be happy to answer questions if you have questions. I think there
Thank
are
you.
some.
Yeah, that was a very interesting presentation. We'll be moving towards the question and answer session now. I'm going to start this with the question and comment from Ala. So his comment is, thank you for your interesting presentation. Do you consider in situ snow observation located in densely forested areas? Some snow observations, for example, from Hydro-Quebec are located near the river coastline, and they are not representative of snow conditions as they melt earlier, and they are shallower than deep snow conditions. So do you filter snow observation based on snow conditions and locations or other criteria?
Mm-hmm. We tried that. It's an interesting question. So yeah, indeed, the snow observations that we have are in different types of areas. So some areas are forested, and SR50 data, they are at meteorological stations. So of course, it's completely unforested in that case. So it's a very big difference. And even with snow surveys, they can be in different type of surface of places. So we did try to kind of do an association or a filtering with that, but in the end we did not do anything because it did not make a difference on the final result. And also retrospectively, we realized that we did not want to filter out data too much because we already have not a lot of data. So that's one thing. We tried to kind of link, yeah, because we use something that comes from the Hydrotel model. The Hydrotel model is, it distinguishes between different types of land use. So we also tried to see if it would make a difference and if we could kind of put in relation the land use of the snow observation with the land use of the grid cell, but it was really not conclusive. And another thing that I want to mention regarding that is that we are working on a 10 kilometer by 10 kilometer grid. So even if your point is at a certain place, on your grid on your grid cell overall, you might have a certain variability of not landscapes but land use. So yeah, I think that's one of the main difficulties with snow. It's just a lot of uncertainty. Yeah, and there is a lot of improvement still to be done to this work.
Yeah, thanks. Next comment is from Martin. So he says, a very interesting presentation. As you were going through, I was about to suggest the shuffle method, and great that you use that. This method is effective resampling using specially correlated random numbers, non-parametric, effectively and empirical copula. So you could also sample using specially correlated random numbers, generally with parametric distribution, avoiding the need for retrospective simulations. Simon Papalexiou has some awesome new tools that account for anisotropy, advection, etc. that could help here.
Okay, yeah, that's a nice suggestion. So yeah, as you can see, we only tried 2 methods for resampling, but yeah, I'm definitely open to try another method because that's actually an important issue. And the more frequently you resample, the more this issue can become a problem.
Thanks. So one thing I was curious about the results are all these results, like for the SRI, they are deterministic or more probabilistic?
They are all probabilistic. So as you can see, I think I can go back. Yeah. Okay. So here you have the CRPS, for instance. So the CRPS is a score to assess the performance of distribution of an ensemble. So everything is an ensemble here. So the particle filter produces an ensemble. So when when I mentioned that we have grids for snow water equivalent, we have 500 of them. So we have 500 particles, so which is a lot. And actually, this is also another problem, because now we have just started trying to insert those grids into the hydrological model, but we cannot actually insert 500 grids. That's just too much. And operationally, the people at the government, they are not interested in assimilating 500 grids. So at the moment, this part that we're doing right now, assimilating the results from that into Hydrotel, it's pretty much deterministic because we haven't figured out what to do with the 500 grids. Okay, so the particle filter as such, it produces an ensemble of 500 members, and you can assess that using the CRPS or whatever method you want. And that's the same or similar with the neural network method that we use to convert snow depth to SWE. So this is also an ensemble. And the size of this ensemble is 20. So we have 20 members. It's written here. So in all cases, we have 20 members. But honestly, this choice of 20 is a bit arbitrary, because it's very easy to have a very large ensemble if you want with neural networks. You just have to reinitialize your neural network. Or you could even have different neural networks with different architectures. There are many ways of obtaining ensembles with neural networks. But yeah, everything is ensembles here. Where we are still wondering how to use the ensembles is after, because we have too many members.
Yeah, I think maybe Martin can talk a little bit more on that, but I think he was looking at that statistical reliability of the ensembles, because if you have just all the ensembles, then it can be very large ensemble, but there must be a way to, you know, like take out those bad samples and just narrow down so it's more practically useful. Moving to the next question, we have a question from Maureen. He says, great presentation. The southern part of the study area has dense network of data than the middle and the northern. How are these accounted to reduce the uncertainty?
I'm not sure it's accounted to reduce the uncertainty. It's accounted for in part by this special correlation that we had. But this is definitely a part where we could have some improvements. And by improvements, I'm thinking about different things. So of course, we could improve the method. So the special component of the method itself could be improved. But another way to improve that, using a completely different approach, would be to try to have more observations in the north. So for instance, so far we have not looked at all at how we could also use data from satellites, but it's another type of data. And also Hydro-Québec, for instance, has lots of GMONs. That's another type of instruments, and they are not completely in the north, but generally Hydro-Québec are a little bit more up north. So maybe there could be ways to add a little bit of data in those areas also. Thanks.
Probably this would be the last question, given that we are coming to the end of the time for today. So it's a comment from Gochang, and he says, this is recently a new data set release, EMDNA. I think it stands for Ensemble Meteorological Forcing Data for North America. And the data provides probabilistic precipitation and temperature data for North America with 100 members. So there are 100 different ensembles. And so could this be a choice when quantifying the input uncertainties?
It could be. What I was waiting for was the resolution. You did not mention it, because what I think would be super interesting is if we could have a finer resolution, because I've mentioned it several times in the presentation. We have a 10 kilometer by 10 kilometer grid, and the basic reason for that is for coherency, because we don't, there's the precipitation and temperature that we have are available at this resolution. So the model is applied at this resolution, and everything is kind of follows that resolution. So if that other new data set would have a finer spatial resolution, it would be extremely interesting.
Yeah, maybe Gosan can correct me, but I think it is available at 10 kilometer resolution, but I will
Okay,
have to
so
double
that's
check.
the same. So this is the same as what we have now. So it could be interesting to compare, because that would be two different ways of representing the input uncertainty. So at the moment, like I said before, to represent the input uncertainty, we use mainly the Kriging variance. So the Kriging is the method that was used to obtain those grids, the precip and temperature grids. So we use the Kriging variance. So now if the other data set is an ensemble, that's another way of assessing the uncertainty. And of course, we could use that. But to me, what I would be especially interested in is if we could have precipitation and temperature data with uncertainty, but at a finer grid than 10 kilometer by 10 kilometer. That would be really, really nice.
I'm just thinking we have a rough data, but at 4 kilometer, but it may not have a lot of ensemble members.
Well, maybe eventually. I'm sure there will be other data sets. Yeah, there are lots of things to test with that.
All right, I think we have come to the end of the webinar today. Thank you again for your presentation and time. That was really interesting. And I also want to thank everyone that attended this webinar. The video recording will be available later today in Core Modeling website. And just a note that next week we'll be having Professor Hamid Morad Khani from the University of Alabama, who will be presenting on hydrological data assimilation. So please stay tuned. That will be all for today. Thank you again, and please stay safe. I wish you a good day. Mary, any last comments you have?
No, I just want to thank you for inviting me. Thank you very much. And thank you everyone for attending.
Bye.
Bye.